Let's take a look at example 9 because I notice again more fractional exponents. So for example 9, we're evaluating the limit as x approaches 1 for x to the exponent 1 over 6 minus 1 over x to the exponent 1/3 minus 1. Again, try out a direct substitution first. If it gives you indeterminate form, that's when we have to do all the crazy stuff potentially. So we're going to do the limit as x approaches 1 for x to the exponent 1/6 minus 1 over x to the exponent 1/3 minus 1. Do a direct substitution for x equals to 1. And if I plug this all in, you end up getting 0 over 0, which means we have an indeterminate form, so we have to think about a change of variable now. So let's start off again by rewriting our limit. The limit as x approaches 1 for x to the exponent 1/6 minus 1 all over x to the exponent 1/3 minus 1. So remember, you've got two different variables, x, with different exponents. Always look for the smallest exponent to work with. In this case, that would be 1/6. So what I'm going to do here is I'm going to take a look at this because we're going to change this now. So on the side, I'm going to say, let x to the exponent 1/6 equal to u. Okay, so that's my first variable change. The next thing that we have to talk about now is recognizing what my variable u will approach. So since I know that x is approaching 1 from my original limit, if I was to plug 1 into my equation here, I know that my u is approaching 1 as well. So I've figured out what my variable u will approach to for my new limit. That's all great. But I notice that I have another x in my equation. That's x to the exponent 1/3. So now what we have to do is we have to think about how can I turn x to the exponent 1/6 equals to u so that I can get x to the exponent 1/3 from it. So if I'm taking a look at this, what can I do so that I can get x to the exponent 1/3 on the left-hand side there? I can raise both sides to the exponent 2 now. So if I do that, I'm going to be left with x to the exponent 1/3 equals to u squared. What I've done here is I've rewritten x to the exponent 1/3 in terms of u, and it just so happened to be u squared. So now that I've been able to make that variable change for x to the exponent 1/6 and x to the exponent 1/3, and I've also talked about what my variable u will approach now, I'm going to rewrite my limit using my new variable. So for my new variable, it's going to be u approaches 1, and then I'm going to have u minus 1 all over u squared minus 1. Oops, that should be in black, not in red, because that's not new. This is the new limit that we're looking to solve for now. So for this limit, again, we notice, I can factor. So I'm going to factor. So that's going to give me the limit as u approaches 1. And I'm going to do u minus 1. And then at the bottom there, that's u minus 1 and then u plus 1. I notice right away that I can cancel some things out. So I'm going to do exactly that. U minus 1 and u minus 1. That's going to leave me with the limit as u approaches 1 for 1 over u plus 1. At this point, I notice after simplifying that if I did a direct substitution for u equals to 1, it's going to work. So I'm going to do exactly that now. So I'm going to plug in 1 for u, and that's going to simplify to 1/2. So the limit as x approaches 1 for x to the exponent 1/6 minus 1 over x to the exponent 1/3 minus 1 equals to 1/2. And again, we had to use a change of variable here so that we could avoid those fractional exponents. Let's take a look at example D now. So in example D, it says evaluate the limit as x approaches 2 for the absolute value of x minus 2 over x minus 2. So in this question, what we're noticing is there are absolute values, and that's what's going to throw us off. So again, let's first start off with a direct substitution method first. So I'm going to do directly substituting. I'm going to do the limit as x approaches 2 for the absolute value of x minus 2 over x minus 2. So I'm going to do 0 minus 2 in the absolute values, and then 0 minus, oops, not 0. It should be 2. Let me erase that part. So that's going to be 2 minus 2 in the absolute values, and then 2 minus 2, and then you get 0 over 0. So again, we've got this indeterminate form, which is no good for us. Now, when we're dealing with absolute value, this is the part where we have to think about creating piecewise functions. So this is going to connect back to day 4 for us when we were graphing absolute value functions. So I need to break up absolute value of x minus 2 over x minus 2 into 2 pieces because of that absolute value there. So I'm going to do that first before I even look at the limit. So I'm going to do that in blue. So I've got the absolute value of x minus 2 over x minus 2. Now remember what I had said. Look at the function inside the absolute value. That's going to tell you what x-intercept or what x value is going to cause a break in my domain for my piecewise function. In this particular case, the function that I'm looking inside my absolute value there is x minus 2. X equals to 2 is going to be the break in my domain. That's going to create my piecewise function. Now, in this particular case, I'm going to make my 2 pieces. Okay, and I'm going to deal with 2 different domains here. I'm going to deal with x is greater than 2, and then I'm going to deal with x is less than 2. We're not going to deal with x equals to 2 here because they'll end up canceling each other out and you have a hole. So we can't equal 2 here. So let's talk about this. If my x values were less than 2, my absolute value function takes on the negative, right? So it takes on the negative. But the bottom stays the same because the bottom doesn't have an absolute value. If I'm talking about my x values that are greater than 2, I'm taking on the original function, which is x minus 2. And then all over x minus 2. And so in this particular case, if I simplify this, they actually cancel out quite nice. I've got -1 when x is less than 2, and then I've got 1 when x is greater than 2. So what I've created here is the piecewise function that represents the absolute value of x minus 2 divided by x minus 2. So we're going to use this now to help us solve our limit. So because this is a piecewise function, it's made up of 2 different pieces. We have to look at the left-hand side limit and we have to look at the right-hand side limit. This one here, that's your left-hand side limit, or what you will use for your left-hand side limit. And this one here will be what you're going to use for your right-hand side limit. So if I'm taking a look at my limit as x approaches 2 from the left-hand side for the absolute value of x minus 2 over x minus 2, I know that that's going to equal to -1 because it's just a constant. So the limit of a constant is just the constant itself. The right-hand side limit for absolute value of x minus 2 over x minus 2, that is going to equal to 1 for us because the piecewise function that corresponds to that is just 1. So the limit is just 1. Now, when I take a careful look at the left-hand side limit and the right-hand side limit, Remember the definition for a limit to exist. Since this is a piecewise function and you're looking at the two limits from the left and the right, they have to equal to the same number. Unfortunately, in this case, they don't equal, which then indicates to me the following. The limit as x approaches 2 for the absolute value of x minus 2 over x minus 2 does not exist. Okay, and the reasoning there, the left side limit doesn't equal to the right side limit. So falling back onto the definition of a limit that we had on day 3. So this is the tricky part about absolute value functions, is breaking it off and creating those piecewise functions. Let's take a look at example 11. All right, so for example 11, we've got kind of the same thing going on. We've got evaluate the limit as x approaches negative 2 for x plus 2 all cubed all over x minus 2 in absolute value brackets. So in this case, I've got my absolute value now in the denominator, okay? But before I do anything, let's try out a direct substitution first to make sure that we do have an indeterminate form here. So I'm going to do the limit as x approaches negative, oops, that should say positive 2 and not negative 2, my apologies. Unless Miss Lim made a minor mistake there, which she did, that should say positive 2 there at the bottom. My apologies. So the question should read, evaluate the limit as x approaches negative 2 for x plus 2 cubed all over x plus 2 in absolute value brackets. My apologies. So we're going to have x plus 2 cubed over the absolute value of x plus 2. So I'm going to do a direct substitution again. So I'm going to do negative 2 plus 2 cubed all over negative 2 plus 2. And that's going to give me 0 over 0. For those of you who are wondering, do you have to show this all the time? Not necessarily. You don't have to show me that it's indeterminate all the time. I'm just showing it to you so that you know why I'm doing all those special things. Because if this ended up giving me something that was just a number, then I don't have to do all of the stuff that I'm doing. But because in each of those examples, when I plugged in the x value for a direct substitution, I ended up getting 0 over 0, which was no good. So because I'm dealing again with an absolute value function in my denominator, I'm going to create my piecewise function to work with. So again, the same thing. I'm just going to use a different color so we don't get mixed up. So I've got x plus 2 all cubed over the absolute value of x plus 2. And now again, look at the absolute value function, or at least what's inside, which is x plus 2. The x-intercept is going to be the break in the domain for us. So in this case, the x-intercept that corresponds to this would be negative 2. Okay, would be negative 2. So I know that I'm going to deal with x is less than negative 2, and then x is greater than negative 2. Don't deal with anything at negative 2 though. So now we need to break it up into our two pieces. Remember, in this particular case, anything to the left of negative 2, my denominator is going to be the negative counterpart instead. So my piecewise function, the first part is going to be x plus 2 cubed all over negative x plus 2. And then anything to the right of that x-intercept, that's going to be the original. So it's going to be x plus 2 cubed all over x plus 2. At this stage, you can probably simplify your piecewise function. You notice that you can cancel things out in each piece. So if I do that, I'm going to end up with the following. I'm going to end up with x plus 2 all squared negative when x is less than negative 2. And then my other piece is just x plus 2 all squared when x is greater than negative 2. So now we have two different functions that we're using for our piecewise function. We have one that deals with the left-hand side, and then we'll have one that deals with our right-hand side. So let's evaluate the left-hand limit and the right-hand limit and see if our limit exists here. So in the first case, I'm going to deal with the left-hand limit. So as x approaches -2 from the left-hand side, for x plus 2 cubed all over the absolute value of x plus 2. Since I'm coming in from the left-hand side, I'm using the function negative bracket x plus 2 squared. So I'm dealing with the limit as x approaches -2 from the left. We're going to do negative x plus 2 all squared. I notice here that if I were to plug in -2 into this particular function, it's not going to cause a problem. So I'm going to do direct substitution now. So I'm going to do negative and then -2. Plus 2 all squared, and that actually gives me 0. So my left-hand side limit for my function is 0. Let's calculate my right-hand side limit now. So coming in from the right-hand side for x plus 2 all cubed over the absolute value of x plus 2, we're dealing with that second function instead. So we're dealing with this one instead. X plus 2 all squared. Again, I notice that at this point, if I plug in straight substitution, x equals to -2, I won't have a problem. So I'm going to plug that in. So I'm going to get -2 plus 2 all squared, and that also gives me 0. So if we compare the left-hand side limit, which is 0, and I compare the right-hand side limit, which is also 0, we notice that they equal the same thing, which means the limit exists here, and the limit is 0. So therefore, the limit as x approaches -2 for x plus 2 cubed all over the absolute value of x plus 2 equals to 0. So with absolute value functions or questions involving limits of absolute value functions, you could get a scenario where the limit doesn't exist, but you also could get a scenario like in this case where the limit did exist. Now that we've gone through all these different examples in terms of how to evaluate a limit either by straight direct substitution, or if we run into the issue where we get an indeterminate form, then we can use techniques such as factoring, simplifying, rationalizing the numerator or the denominator, using one-sided limits in cases where we're dealing with potentially piecewise functions, or a change of variable if we're ever dealing with rational exponents. So remember to practice evaluating limits algebraically. It's probably the bulk of this particular unit, so make sure you practice